and get started. Um, just gonna go over the 2023 exam because I feel like that's the harder one of the exams that you guys got. Uh, but yeah, this one's a bit of a bastard. So, but I mean, some of these questions are pretty reasonable. So like this kind of question, I expect to show up, where they give you like the cycle and all that jazz. This is pretty standard. But we'll go ahead and there's a couple questions in this test where I don't think they're gonna do that because I think that's not like I don't think you guys have covered enough or even like learned some of the stuff to cover. So if I see a question like that, I'll skip it. But yeah, so let's go ahead and get started then. So if we look at the diagram shown here, what's the here? It shows an order and structure of the intermediate citric acid cycle. Each reaction is indicated by number 1. Yeah, 1 through 8. Cool, great, great, great. Use a diagram to help follow the. Okay, cool. Yeah. So if you see a diagram like this, they most likely want you to do a couple of different things. They probably want you to track carbons and to maybe uh, track carbons and most likely say if you put some sort of intermediate in, where does it go? So like if I put glutamate or something, like if I put where's alpha ketoglutarate? Like they'll ask you to try and figure out the enzyme or something like that. So expecting a question like that. Uh, but this question, no. So I think there is maybe a way you could reason through this, and if we have time at the end, I will come back and try and reason through it. But this is a question I had to stare at for a very long time to actually figure out, like, because there's two options for this question. I'll give it away a little bit. The one option is that you upregulate citrate synthase if you've done this exam, and that would increase the amount of yield of citric acid, right? Because citrate synthase makes citrate. And the other option is that you downregulate aconitase, right? And if you downregulate aconitase, you would drop the amount of citrate that is being turned into isocitrate, um, and that would also show this graph. But the answer is aconitase. I'll just give it away now. The answer is aconitase, and I'm pretty sure the answer has to do with how steady state equilibrium works and the speed of the reaction for aconitase versus the citrate synthase. The rates are different, but I won't. I'll cover that later if you have questions on it. Or we're gonna move past that one because I don't think that one's reasonable for what you guys have covered. For 440. Yeah. Now I don't know if I trust your prof though, because he's a bit mean with some of the questions, but we'll see. Um, so for this, now these are steps you can do. Or these are questions you can do. So if we inhibit which step in citric acid would most likely lead to an increase in the amino acid aspartate. Okay, so you'll learn about this a lot more in 441. And there was a question on this, similar to this, on the 2024 exam, exam 3, the one that I took. And if you remember, what is the structure of aspartate, right? For aspartate, we have this kind of, and watch me draw it wrong now as I speak about it. We have our little O up here, right? HO. We've got our NH2 group, and then we have our carboxyl group. And if you were to draw this in this kind of form, right? What you would see is that if we were to look at this carbon, so we'd have our CH. If we have an H2N here, we put a COO minus up here. And then we have 1 and 2 carbons, so 1 carbon, CH2, and 2 carbons, which is where our COO minus is. Which structure in here looks similar to this? So, no, not the one that I circled, but there's... We can be a bit too easy. Which structure looks... Okay, so malate looks pretty similar, right? Is there another one that looks similar? So oxalate, these two, right? Now, I think they would have to give you like the type of reaction that they would expect to see here, because I could totally see the argument that it would be malate, right? But for this question, it would be oxaloacetate, because there's a specific enzyme, and they have to give you the enzyme in the question. For some reason, if you see a question like this and they don't tell you like what the enzyme is, right? Just know that if you see this like ketone group, this carbonyl group here, and you see an N, these two things can be interchanged. There's an enzyme called transaminase. You guys don't have to know that for 440. But on my exam, they gave us the reaction for transaminase, and they were like, where does glutamate feed into this chain? So they could totally do that, where they say give you a reaction, right? Where they say like glutamate plus water equals alpha ketoglutarate plus something else, plus an amine, right? And they can say, where does the glutamate feed into the chain? And they can do the exact same thing with aspartate. They can do like aspartate plus water makes oxaloacetate and amine. Where does that go into the chain? And you'd have to put like an arrow here that says that, basically, something like that. Does that make sense? No. No, you're okay. What's the problem with it? Yeah. Briefly, right? So aspartate and oxaloacetate, the only difference between these two compounds is this carbonyl group and this amine group, right? In 441, there's an enzyme called transaminase. It's not very important for this course, but what I'm saying is that they could give you a question where they're like, here is a reaction where aspartate plus amine or aspartate plus water makes oxaloacetate and ammonia. And they could ask you, where in this cycle, does that aspartate turn into an oxaloacetate? And you'd have to put an arrow that goes like here, and you'd have to say aspartate, right? Like over here or something. So it's like it's like where does this thing feed into the chain? Is all it is. I don't expect them to do this. But I don't trust him, so we'll see. So if I was to say what step, I would just say step inhibiting which step would most likely lead to an increase in the amino acid aspartate. I'd probably say if you inhibited this, because that would lead to a buildup of that, and then this can go in this direction as well. But they'd have to give you a little bit more information, like I said. So if that didn't make any sense at all, don't worry. They'd have to specify a bit more. So I'd expect it to be step one. This next one, though, they can totally test you on. So this is just a classic carbon tracking question, and these are very reasonable. So if you know how carbon tracking works, right? So if we have acetyl-CoA labeled with C14 on the methyl carbon. So the methyl carbon of acetyl-CoA is this one, and they've nicely labeled it for you. What percentage of oxaloacetate molecules will be labeled as shown? So you have to put like 0, 150, 25, whatever, right? I'll just go say it right now. There is no world, pretty much, where it's going to be 25 or 75. Unless you are in the second cycle. Then there's some weird shenanigans that happen. But generally speaking, especially for this exam, I hope, and they seem to have learned their lesson from the last test, I hope, that they need it's most likely going to be a first cycle question if they ask you to track carbons. They'll most likely tell you, okay, if we label this carbon here, where does it go? Maybe they'll label the S. I don't know. They could label whatever they want. But if we label this C, where does that C end up in citrate? So let's start with that. Which carbon in citrate corresponds to this carbon here? This one or this one? Top one or the bottom one? Top one. So the top one. Okay. And then we go down. Which one? It can't be the bottom one in this case, because this is that's that bottom carbon there. Yeah. You're right. I mean, it is a bit weird because they look like they're symmetrical, right? But on the first cycle, we know exactly where that carbon has been added to, because only one of them is labeled. We only circle both if we don't know where the label has ended up, right? But we know 100% of the time the label is going to be on the carbon that we labeled it on, right? So if we go down, where's the next, which one's this one as well, right? And I'll just go ahead and go through. So this one, this one. Now this is where we turn into like the thing where we have no idea. So this, we are now through the cycle. We're 5 steps through the cycle. And at this point, I have no idea because this molecule is symmetrical. So this molecule is symmetrical. I can't tell which side is which. So in this case, it could be either this or that. And I have no idea which one it is. Same thing up here, this or this. Same thing here, that or that. And then same thing up here, this and that. So now I just have to go down and I have to go through and figure out what is what. So is there a case where I'm going to have oxaloacetate labeled like that? Well, if we go back and look at what I drew up here for oxaloacetate, which is this up here, there is no situation where this top carbon is radiolabeled, right? So this is 0%. And you technically should put percent here because they're sticklers for that, but I'm not going to put it because I'm lazy. This here, is there a situation where I'm labeling that carbonyl? Yes, and one out of the two possible labels is that carbonyl. So I expect this to be 50% because, like I said before, we have two options for our label, but there is no preference for the label to be in one spot or the other, right? There's no thermodynamic favorability for it to be on the carbonyl carbon versus the carbon next door. Right? So because there is no preference there, it's going to be a 50-50 mix of if it's on the carbonyl carbon or the carbon next door. Does that make sense to everybody? Okay. And so if we go to this next one here, we said this before, it's going to be labeled on that carbon as well. So this is going to be the other 50%. Right? So we already talked about this. This one we said there's no situation in oxaloacetate where it's down in that bottom carbon. I'm going to come back to this one because I think this will trip people up a bit. And then we'll go ahead and look at this. There is no case where both the top and the bottom carbon are labeled at the same time. What is going on? There's no case where both the top and the bottom carbon are labeled at the same time. At the same time, right? That's what makes these two weird, because they're suggesting that there is a scenario where both carbons, there's two carbons labeled at once, which is not going to happen unless you do a second cycle. So we can say that this one is 0, and this one trips people up a lot because they look at it and say, well, up here I circled both of these, and they circled both these here, so why is it not 100% here? It's not 100% here because we only have one radiolabel going in. We only have one carbon that's radiolabeled. We only did this thing where we circled both because we don't know which carbon the radiolabel ended up on. Not because the radiolabel split in two and magically divided. It's because we don't know which one it is. So there's never a case where the radiolabel is going to be on both carbons at the same time. Does that make sense? Yeah? Yep. Okay, cool. If we move on here. And this is just a classic, do you know what happens in the reaction? How many steps make CO2 in citric acid cycle? Which steps are they? 3 and 4. Isocitrate dehydrogenase and alpha ketoglutarate dehydrogenase. So steps 3 and step 4. What else do step 3 and step 4 use and make? NAD. NAD plus goes in and makes NADH. Right? What other step makes NADH? Yep. And then which one makes FADH2? Succinate dehydrogenase, right? Good. Which one uses CoA? Yeah, step 4. Right, succinate CoA synthetase uses CoA. So, yep. Or sorry, alpha ketoglutarate dehydrogenase. Sorry, not that succinate CoA synthetase is this one. It's the one next door. Thank you. Good catch. Okay. Moving on, we have this one here. So if we look at this, it's a continuation of part one, but sure. So you are studying pyruvate dehydrogenase, okay? Citric acid cycle, two different strains of bacteria, X and Y, great. You grow each strain in a media under three different conditions. So condition one, everything for aerobic respiration, great. So just a normal standard control. For condition two, we're looking at the control media plus the inhibitor, which is an analog of acetyl-CoA. So I think this is important. So the fact that it's an analog of acetyl-CoA. So that probably means it's a competitive inhibitor for PDH, if I had to guess. I'm not too sure. I mean, I haven't seen this before. I don't think it was covered in your lecture, the specific compound, but because it says it's an analog of acetyl-CoA, you can make the assumption that it's a competitive inhibitor for pyruvate dehydrogenase, because pyruvate dehydrogenase, right, has a feedback inhibition where the products from pyruvate dehydrogenase inhibit itself. And then in control media 3, we have oxalomalate, which is an analog of alpha-ketoglutarate. So the same thing here, where this is going to inhibit alpha-ketoglutarate dehydrogenase.
So when it says
If it says it's an inhibitor, that's an analog of the thing, then it's a competitive inhibitor, right? Because it has the same structure, very similar structure, and it's an inhibitor. So it has to be competitive in that case, most likely. So now we look at the graph, and we have CO2 production in three different conditions. Pretty straightforward. If we look at the different conditions, right? So if you look at the control, the weird thing is that strain B is missing a CO2, or either that or strain A has an extra CO2. What are the reactions that produce CO2 in this chain? So 3 and 4 from citric acid do. Is there another one? PDH makes one. So there's 3. So I expect there to be 3 CO2s released, or 3 moles, or 3 nanomoles, or whatever, right? I don't care if it's nano, right? It doesn't matter if it's nano or not. It still would release 3 moles of CO2, and then if you scale that down, it would be 3 nanomoles, right? So the control, right, in strain A releases 3 nanomoles of CO2, which makes perfect sense, right? 1 from PDH, 1 from 3, and then 1 from 4. Strain B is weird because strain B is missing one of them. So we can already answer question A based off of that. So the control results indicate that 1, 2, or 3 reactions that produce the molecule blank is missing in strain B. So clearly we're missing a CO2 here, right? So we're missing 1 CO2, and that is the answer to that. For part B, the fluoroacetyl-CoA results indicate that normally the enzyme blank is more or less active, or equally active in strain A compared to strain B. So if we look at the fluoroacetyl-CoA, we see that there is just there's nothing produced. There's no CO2 produced. And I said that fluoroacetyl-CoA is an inhibitor, a competitive inhibitor of pyruvate dehydrogenase, right? Because it matches the structure and it's an inhibitor, right? That matches the structure of acetyl-CoA, and acetyl-CoA is an inhibitor of PDH. So the fact that both of these two strains are inhibited to the same level, right? They have the exact same level of inhibition, suggests that normally the enzyme PDH, so pyruvate dehydrogenase, is equally active in both of them because they are both inhibited to the same level. If they were not active, to the same level, I would expect to see some difference here in the CO2 production. Does that make sense? Yeah.
how do you say again that's kind of PDH?
Which one is the? Because we said that it's an analog of acetyl-CoA, and we know that acetyl-CoA is an inhibitor of pyruvate dehydrogenase. Because it's an analog of acetyl-CoA and it's an inhibitor, we're thinking that it also has to inhibit pyruvate dehydrogenase. Does that make sense? Okay, does the logic I used for this make sense? Yeah?
One percent. It's what? Say
Yeah, so I have to think about that. So if fluoroacetic results indicate that, so if you're saying if strain A had more CO2 production, yes, because I know, right, that if I know that this thing is an inhibitor and I'm still producing that one CO2, even though this thing is supposed to be inhibiting, that suggests that it is more active. Does that make sense? Okay. Yeah, this is a bit of a weird one. I again, could he ask this? Sure. Um, it's reasonable, right? I can't really say much more than that. But yeah, does that make sense to everybody else? Yeah, makes sense. Okay. And if we look at, so that, yeah, the oxalomalate data together with the control and the fluoroacetyl-CoA results indicate that the enzyme blank is missing in strain B. Okay, so if we look at oxalomalate, which enzyme is oxalomalate inhibiting? Alpha-ketoglutarate dehydrogenase, right? Yeah? So it's inhibiting alpha-ketoglutarate dehydrogenase in this case. And so,
So they're both the feedback. I'm sorry.
yeah, yes, in this case you can think of it like that. I'm trying to remember how this, so if it's analog alpha-ketoglutarate, yeah, so this one, right, alpha-ketoglutarate, this is not really a feedback inhibitor. In this case, what is happening is this analog of alpha-ketoglutarate is going into the active site of alpha-ketoglutarate dehydrogenase, and it is stopping the enzyme from working. That is what. So it is a competitive inhibitor, right? But it's not really a feedback inhibitor, because a feedback inhibitor is like you make the product, and the product comes back and inhibits. That's what PDH is. So PDH does that. PDH makes acetyl-CoA, and the acetyl-CoA comes back and inhibits. This is not that. This is like a substrate level inhibitor, if that makes sense. Does that make sense to everybody? Okay. So if we look at the oxalomalate data, we can say that, okay, so in this case, alpha-ketoglutarate is inhibited. And if alpha-ketoglutarate dehydrogenase is inhibited in both of these strains, we can see that for strain A, we are clearly missing a carbon produced. But in strain B, we have the exact same level in the control and the oxalomalate. So what that means is, because we're looking at this and we're seeing that the oxalomalate condition has the same CO2 as the control, and with the oxalomalate condition, we inhibit alpha-ketoglutarate dehydrogenase, the enzyme that is missing in strain B is alpha-ketoglutarate dehydrogenase. Yeah? So I'm going to say AKG, because I can't write the whole thing. Does that make sense? Any questions? You look like you want to ask a question.
Think about it.
Yeah, yeah.
It's like we're stopping that point, right?
Yes.
How does that that enzyme is
So if you look at the control, right, there's no inhibitors, right? Nothing is wrong. So we can go through the cycle perfectly fine. And we're still only producing 2 CO2s, right? If we look at strain B.
I think I get it.
You get it now, okay. Okay, just to reiterate though, right? Because we go through this first cycle and we're only producing 2 CO2s, or we go through the cycle and we only make 2 CO2s in the control. Now we go to the oxalomalate condition, and we can see that if we look at strain A, we only have 2 CO2s being produced. That makes sense, right? We're inhibiting alpha-ketoglutarate dehydrogenase, which is supposed to produce a CO2. But if we look at strain B is also missing a CO2. But the thing is with this is that this level is the exact same as this level, which means that there is no difference in CO2 production between the control version of strain B and this inhibited version. So that suggests that the enzyme that is missing or broken is alpha-ketoglutarate dehydrogenase, because the level of CO2 produced in both of these strains, whether it's inhibitor or not, or in this same strain, whether it's inhibitor or not, is the same. Yeah?
Just a brief.
Yeah.
I don't.
These three, yes. Okay.
Steps is what ISIS.
Yes. Yeah, you can. Yeah, you totally could. I think, let's see here. Yeah, so you're saying if oxalomalate was an inhibitor of like isocitrate dehydrogenase instead, yeah, then I would expect both of these, all of these to go down. Like these would go down, this would also go down. Um, yeah, that would only be the case if the control also had the defect in isocitrate dehydrogenase, though, right? Because I could have a case where it's alpha ketoglutarate dehydrogenase and this is still up at 2, but these two are chopped in half. So, but I think that's kind of like a weird question though. But so yeah, yes, yeah. I'm gonna say yes to everything you asked me about. Do I think they could do that? They could do anything they want. So yeah, does that question make sense though? I think these are some of the harder questions. To be honest with you, I think these are a bit more challenging. There's one more I think at the bottom that's a bit mean. Okay, for okay, yeah. So for this one, for part 2, the curve shows oxygen consumption rates measured from isolated mitochondria in the presence of ADP and PI. Okay, I'm already thinking about some weird electron transport chain thing here, because why on earth would they mention ADP and PI, right, if they're not going to talk about electron transport chain ATP synthase? Okay, so using the following list, write the number in the blank for the molecules added to each time point to get the observed result. Okay, so we've got a bunch of things, and we've got some O2 consumption graph. Where is O2 consumed in this process? ATP synthase, does that consume O2? What consumes O2? Complex 4. So complex 4 consumes O2 to make what? Water. So we're making water using oxygen gas. And where are we getting the electrons from? The donors, which come from what cycle? And PDH. Yeah, so all three of them, right? All three of them make electron donors. Which one makes FADH2? Citric acid. How many NADHs in citric acid? 3. Yeah. How many in PDH? 1. And then how many in glycolysis? 2. Right, yeah. So two, yeah, I am pop quizzing you. 2 electron carriers, right? Because each pyruvate goes through each pyruvate. 1 glucose makes 2 pyruvates, right? And then each pyruvate, to make 1 pyruvate, you have to go through that glyceraldehyde 3-phosphate dehydrogenase step. And so each one makes an NADH. And you have to think about that for citric acid cycle as well, right? Because if you are making 2 pyruvates, the number of NADHs and FADH2s you make for 1 glucose doubles. Because 1 glucose makes 2 pyruvates. Those 2 pyruvates both turn into acetyl-CoA, and each one of those uses 1 NADH, or makes 1 NADH, right? So that's 2 NADHs there. Every pyruvate that goes through citric acid cycle makes 3 NADHs each and 1 FADH2. So that'd be 6 NADHs from citric acid cycle, 2 FADH2s from citric acid cycle, 2 NADHs from PDH, and 2 from glycolysis. Right?
So we would literally just cut that in half.
If you're looking at 1 pyruvate, you cut it in half.
And that's get rid of the 2 from glycolysis.
You'd have 1 from glycolysis, though, right? Because each one, right? Yeah. So the difference between a glucose molecule and a pyruvate molecule, or an acetyl-CoA molecule, that does matter. That's not important for this question, but I wanted to quiz you guys a little bit, see if we can remember all that stuff. Being able to pull out that stuff on the fly is really helpful on the exams. You guys only have 45 minutes. There's not a lot of time. So, yeah. Yeah, man. Okay. Anyways, so these are just like, these are things you should memorize, to be honest with you. Like, so specifically I say like rotenone you need to know and cyanide you should know. Cyanide inhibits what complex? 4. Rotenone? I'm pretty sure it's complex, let's see, I think it's 1 if I'm not mistaken. It's an NADH, it's an NADH dehydrogenase inhibitor. NADH dehydrogenase is the first complex. It's complex 1. I believe there was a slide on different inhibitor types. So like, the trinitro DNP is one of them, right? The uncoupler. But rotenone is one of the ones I would keep in mind as one of the main ones.
That one is which?
Rotenone is complex 1.
And that's
Is complex 4. Yeah. So if we look at the graph, we can see that we start going from 0 to 1, we have a large amount of O2 consumption, right? So if we are consuming O2, that means what is happening to the electron transport chain? It means that we are going through the electron transport chain, right, and we're using up our O2. So if I know that cyanide's an inhibitor, right, I'm not going to use O2 if I inhibit it. So this is gone. Succinate, I could see succinate being an answer. Rotenone's an inhibitor. And now I'm looking at these two. Which one can I eliminate off of this? I guess, like, let's talk about glucose. Does glucose work here? Why does glucose not work?
Just like how they like basically and like causes
I mean, it can. It can.
because glycolysis happens.
And where are we right now? We're on the mitochondria. Isolated mitochondria. Read the question. Yeah. Isolated mitochondria means that we cannot use glucose because glucose has no way of being turned into anything if we don't have our cytosol and our cytosolic enzymes. That is why that's why reading the question is like really important for these tests because they sometimes like throw in nonsense like that. Okay, so now we have malate together with pyruvate and succinate. So which one is the better answer here? 2. Why is this a better answer than succinate for this case? Usually it's just more NADH, right? And there's actually, I'll show you later on in the question, there's another reason, but yeah, so we'll go with 2 for now, right? So we know it's either 2 or 4. I'll put 2 or 4 for now. So at time 1, we have now entered this state. We have no O2 consumption. So what does that mean? There's no O2 consumption. So it could be cyanide. So we know it has to be an inhibitor, right? That's what we're saying. So we agree it has to be some sort of inhibitor, right? We're all clear on that. If we're stopping O2 consumption, so it has to be either cyanide or rotenone. So 3 and 5 are the 2 options that we have. Let's look at time 4. So at time 4, we can see that we have this period where we have no O2 consumption, but then suddenly we start using up O2 again. So it cannot be. Why can't it be cyanide? You're right. It cannot be cyanide. Yeah. Yes. So if it's inhibiting complex 4, there's no way we can do any sort of O2 kind of like there's no way we can have any sort of O2 consumption if it's cyanide.
Is that why then for time 4 it would be succinate as opposed to 2?
There you go. Yeah. So this is going to be 4 times 0. We can only have one thing per. It's going to be 2, and then time 1 is going to be what? Not 5. Said it's going to be 3 because 3 inhibits complex 1, which does stop the NADH. It does stop the 4 protons being pumped from pump 1, but it does not stop 2 and 3. So we can still go with our O2 consumption from there. Does that make sense? So succinate goes to which complex in electron transport chain? 2. So it's complex 2 is succinate dehydrogenase. It's the same. So citric acid cycle, right? Succinate dehydrogenase. Complex 2 is the same enzyme. So that's something else you should know is that succinate dehydrogenase from citric acid cycle is actually membrane bound. It's a membrane bound protein. It is bound to the mitochondrial membrane, right? Question?
Yeah, it's kind of like a different question.
Uh-huh.
There the section you were asking, like they were telling us which enzymes we should know as transmembrane and then cytosolic. Are you able to explain that?
Depends. There's a lot of enzymes for membrane bound versus cytosolic, right?
Just the electrophortation.
Well, in the electron transport chain, most of them are membrane bound. Did they say specifically which ones are
No, they never said like which ones are.
Okay, so generally speaking, the enzymes in the electron transport chain are membrane bound. Complex 1 is membrane bound, complex 2 is membrane bound, complex 3 is membrane bound, and then complex 4 is membrane bound. So I'm not too sure what they mean by like which ones are membrane bound in electron transport chain, because they're all membrane bound in the electron transport chain. The only ones I can maybe see them arguing are like the quinones. The quinone and cytochrome C, those like move around. So they're not like bound in the membrane, but they are like, they kind of do stick in the membrane. But they do move. So I wonder if that's what they were trying to get at. But like so cytochrome C, right, goes from complex 3 to 4, and then ubiquinone, right? Not ubiquinone. Yes, ubiquinone. No, Q. I think it is ubiquinone. I'm mixing it up with ubiquination because it's like a separate thing. But ubiquinone, right? So those two are like, they're not like bound to the membrane, quote unquote. They do move around in the membrane, but they are like, they can only be in the membrane. They don't really move anywhere else. So yeah. Okay, so that question makes sense, right? You kind of had to like go through the whole thing to get to the actual answer, but that makes sense to everybody how we got to the 2, 3, and 4 as the answers there. Okay. Yep. And then I didn't bring my water with me. Oh, it's okay. All right. This one should be some free points. I'm gonna be honest with you. Number 2 should be like, you look at this and you say, "Hallelujah, Hurley has blessed us today." Okay. So if we look at number 2, and it's just a bunch of true false stuff. Welcome in, guys. So glad you could make it. You've graced us with your presence for once. Okay. Yeah, no, you weren't. Anyways, yeah. So we already went through like most of these questions up here. I can take questions afterwards. People have more questions on them. Um, but yeah, if people have questions on this, I'll come back to this and try and answer this. But I don't think it's going to show up on your exam. All right. 2. So here we have, just realized that my thing is not charging, but I'll try and go through it first. Okay. So uncoupling ATP synthesis from electron transport can be done by adding a molecule such as DNP to a purified respiring mitochondria. Okay, so we're just talking about uncoupling. Nothing unusual there. Indicate your understanding of uncouplers with these statements. I'll let you guys go through them real quick while I plug this in, and then I will discuss them after. There we go. All right. For the sake of time, I'm just going to go through them. But so in actively respiring mitochondria, addition of an uncoupling molecule will blank the rate of oxygen consumption. So if we add an uncoupler, what uncouplers do is that they get rid of the proton gradient. So all of the work that your electron transport chain enzymes or proteins have been doing to kind of make that gradient is just being screwed up by these uncouplers. And so if the gradient is being dissipated, your pumps have to work harder to maintain that gradient, and therefore we must have more electrons being dumped into oxygen per minute or per unit time. Does that make sense? So I would expect the rate of oxygen consumption to increase with the addition of an uncoupler. Good? Okay. In actively respiring mitochondria, the addition of an uncoupler will what the pH of the mitochondrial matrix. Okay. The mitochondrial matrix, what is the mitochondrial matrix in terms of pH? Where are we pumping our where are we pumping our protons into from the electron transport chain? Into the intramembrane space. And so if we have a situation where the uncoupler, what is the uncoupler doing again? It's breaking the gradient by doing what? It puts it back into the matrix. And if we're putting H plus into the matrix, is that making it more acidic or more basic? Acidic, right? So the pH of the mitochondrial matrix will decrease. It's dissipating the gradient is how we refer to it. A gradient is when we make a thing we have high concentration on one side and low concentration on the other side. An uncoupler dissipates the gradient by taking things from the high side and putting them into the low side. Okay, so in actively respiring mitochondria, the addition of an uncoupler will increase, decrease, or not change ATP synthesis. Decrease. Why is it decrease? Exactly, right? So the gradient is being dissipated, like we said, and therefore if you have less H plus for ATP synthase to go pull it down this gradient, you can make less ATP. So, relatively straightforward. Just gonna double check. Yeah. Okay, this is a very Bio 200 question. I'm gonna be honest, this is a very Bio 200 question. Takes a little bit of problem solving skills, but we'll work through it, and hopefully it'll make sense by the end if you didn't get this one. So we have 4 electron carriers. Cool, I don't care what their names are. Required for respiration, bacterial electrolyte transport chain. We have the oxidized and the reduced states. Determined by measuring absorbance of light. Okay, yeah, cool. Don't care. You're asked to determine the sequence of carriers within electron transport chain, and you add a substrate, oxygen, and you use 3 different inhibitors. Okay? And your results are here. So if we'll look at the inhibitors, and we'll look at them in rows for this. I want to know what each inhibitor is doing. So if we look at inhibitor 1, carrier W is reduced, carrier X is reduced, carrier Y, and carrier O are oxidized. Right? Does that make sense? So the fact that I have 2 things that are reduced and 2 that are oxidized tells me immediately that this is in the middle. Because that's not possible otherwise. Because if you remember how electron transport chain works, right? If we reduce one carrier, and then we reduce the other carrier, and then we inhibit it, anything after that is not going to be reduced. It's going to be in the oxidized state. Yeah? Does that make sense? Okay. So this is going to be inhibitor 1. So I also know, based off of this first kind of section, that carrier W and X have to be on this side and not at the end of the chain. Because if they were at the end of the chain, I would expect them to be in the oxidized form, not the reduced form. Does that make sense? Yeah? Okay, trying to make sure I keep everybody on track here. So this side's going to be Y and Z then. So you actually got a lot of information from that first trial already. So if you look at inhibitor 2, we see that carrier W, carrier X, and carrier Z are reduced. Carrier Y is oxidized. So if carrier Y is oxidized, where is carrier Y going to be placed in this? At the end, right? Carrier Y is at the end. Why is it at the end? Well, and I think, is there another explanation, like a better explanation for why that is? It's not inhibited, it's not being reduced. Right? So the fact that we're reducing all the other 3 and not reducing inhibitor Y, not inhibitor, God's sake, we're not reducing carrier Y, tells me that carrier Y is most likely at the end. Because if the other 3 are reduced and Y is not, that means that we're still yet to get to Y. Does that make sense? What is someone who is it? Nestor? Who is it? Bruh. What does she want, bruh? Okay, so that's gonna be Z, and this is gonna be inhibitor 2. Make sense so far? There, we're following along. Okay, and then by process of elimination, this has to be inhibitor 3, but that doesn't tell us what the order is of these 2. So you're saying X is the first one being Y is X the first one? Yeah, so it's being reduced before anything in the other 3 are oxidized.
Could we compare these to actual electron carriers?
Yes. Yeah. Oh, I see what you're saying. Like actual, like genuine electron. Oh, I don't know if you can compare them to like actual. You can compare them to the complexes. I think if you wanted to do that, you can compare it to like complex 1, complex 2, complex 3, complex 4. But I think this one's a bit. This one's a bit, yeah, you can't really compare it directly to the different electron carriers because like complex 2 like takes a separate electron carrier from complex 1. So it doesn't go from complex 1 to complex 2 to complex 3 to complex 4. It goes from complex 1 to 3 and then 2 to 3. And then they both go to 4. So you can't really directly compare them. Does that make sense? All good? Okay. Okay, this is just a bunch of math.
Was that we're not gonna have like a lot of that?
This is reasonable for the amount of math you're going to get. You're probably about a page is reasonable.
I didn't sign up to do that.
I think, well, calculus is actually one of the requirements for doing. So I think it is, yeah. And it is for PChem. You have to take calc, I think, or at least some calc, I think. But no calc 3. Oh yeah, well calc 3. You need calc 3 for the major. The biochem major requires calc 3. Yeah. Anyways, for this question, this is. I hope he gives you numbers like this that are actually reasonable and not like the nonsense he gave you on the last test.
That was mean.
Yeah.
I think 2,300.
There were some pretty mean numbers. I think if you had an extra 15 minutes to do that exam, maybe you get more. Probably you get a lot more of those. But you didn't have an extra 15 minutes, so it's not really easy to do that. But these first, so A is actually relatively straightforward. So A, we're just looking at the concentration and what is the cellular ratio of fumarate to succinate divided by succinate, and what is the E naught or E prime for the half reaction. So show your work in the given units. So if we look at that, so the concentration is going to be fumarate, which is this 5, divided by succinate, which is that. And what is the E for the half reaction? So if we just do 5 divided by 10, or 5 divided by 50, right? 5 divided by 50 equals 0.1. What are the units for this? Nothing. There's no units because the millimolars cancel out. So, yeah. Well, I mean, there's more in the question. The question has more. Yeah, you probably get 2 points there if you did that. Yeah. But the question is asking for. And I always forget this equation, but you do have it on the bottom, I believe. Yeah, this equation. You need to use this now for that because it's asking about the E prime, and you're given the E naught, and you also just calculated the ratios here.
Oh, it's plug and chug.
It's plug and chug. Yeah. It's gonna be. Let's see here. If I'm not mistaken, do they? That's actually kind of weird that they did that. Huh. I think you guys can just say it's 100. Yeah, I wouldn't bother with this 96,500. I think is what it is. Yeah, I wouldn't. I don't care. I don't care. But you can just plug in chug here. So you can just say that E prime is going to be equal to 0.05, which is the E prime naught. I'm going to get rid of the units to make it simple. 5 divided by the number of electrons times 100, which is Faraday's constant, log of the electron acceptor over the donor. Yeah? Does that make sense? And so now if we just simplify this expression, we have E prime equals 0.05 plus 5 divided by N is what in this case? Number of electrons, 2. And we got 2 because of this. There's 2 electrons here. So it's going to be 2 times 100, which is 200. And then that's going to be that log of acceptor. I don't know why I just did that. Acceptor divided by donor. Why did I put the double parentheses up here?
Except your donor is the 0.
Yeah, yep. And it's like that because it's like that because the acceptor divided by donor, they could theoretically ask you to calculate donor divided by acceptor and then tell you to switch it. Does that make sense? They said do let's see here. Yeah. I just need to double check that. But so we did fumarate divided by succinate, right? And fumarate is the acceptor here. So fumarate is accepting 2 electrons, and succinate is like donating those 2 electrons. Does that make sense? Yeah. And so what they could do is they could ask you to calculate succinate over fumarate instead, but then you have to switch the ratio because the question is asking you for acceptor divided by donor.
Just switch the ratio.
Yeah. I mean, so if they asked you to do succinate over fumarate, it'd be 10. But because you want to do acceptor divided by donor, fumarate is the acceptor, so you'd have to do 5 divided by 50 instead. I'm just saying that they could reverse it and they could ask you to calculate the other ratio, but you have to actually use the acceptor over donor.
Well, it just makes sense.
They could just try and mix you up. Does that make sense what I'm saying there? Yeah, makes sense? Yeah? Okay. They haven't done that here, thankfully, but we just have to do the math here. So acceptor divided by donor, we said this is 0.1. And then if we just do the math for this, so how much of this do I remember? So 5 divided by 1, 200 divided by 5 is like 40. Which one? Oh, yeah, they do. Yeah, perfect. Yeah, so very conveniently, they've given me the number up the top. This is why you read, guys. so yeah, so this is going to be E prime is equal to 0.05 plus 0.025. Log of 0.1 is what? -1. Yep. And so this is going to be equal to 0.05 plus 0.025 minus 0.025, which is just going to be equal to 0.025. Yes. So that would be your answer, and it would be in volts. Yeah. Okay. And you're going to do the exact same thing for the one underneath. So in this case, we're doing it for use the concentration above with a cellular ratio of NAD plus to NADH. So NAD plus is 3, NADH is 0.3. 3 divided by 0.3 is 10. What are you doing? What is this guy doing? What can you think? What you say 1?
Wait, what?
Did you say 1? Okay. So 3 divided by 0.3 is 10, right? So the ratio of this would be 10. So NAD plus to NADH is going to be 3 divided by 0.3. Put your units. Don't be like me. Put your units. Is going to be 10. Don't be like me. So it's going to be 10. And then we do the exact same thing where we use this equation. I guess I'll go ahead and just write it out, but I think you guys get the idea at this point. So this is going to be negative 0.30. It's going to be 5 divided by n times 100 log of the acceptor divided by the donor. And in this case, the acceptor is NADH, which is the hold on, I just realized. Oh, did they switch it around for this one? They didn't, right? It should be the same. Yeah. Yes. NAD plus is the acceptor. I don't know why I'm tired, man. Okay, the acceptor is NAD plus, guys. It's NAD plus. So NAD plus is 3. It would be divided by 3 divided by 0.3. Okay, so it would just be 10. You do the math from here. N is going to be 2. Make sure you check what N is. Sometimes it's not 2. They could just say it's 5. Just whatever they decide. Just a case of read carefully. But yeah, so we do 5 divided by that. Very conveniently, that's also 5 divided by 200. So it's just going to be negative 0.3 plus 0.025 times 1 is equal to E, right? And then this would just be, I have to make sure I do my math correctly here. So E prime would be equal to 0.275 volts.
For negative.
Yes. Thank you. Yeah. So negative 0.275. Coolio. And then for the very bottom one here, it's just what is the delta G prime for oxidation of succinate, yada, 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 yada. The equation for this is going to be delta G, I'm just going to put G equals negative N, Faraday's constant, times E of the reaction that you're doing, right? And so to calculate the E here, we're going to do, is it E prime here? I can't remember off the top of my head which one it is. It's the E prime. It's one of these. It doesn't really matter which one you do for this case. But we're going to do that. It's going to be E prime or whatever equals the E of the acceptor minus the E of the donor, if I'm not mistaken. Right? So if we do acceptor minus donor, the one that is doing the accepting in this case is going to be, so NAD plus is going to be one doing the accepting in this case. So NAD plus, the reduction or the value of NAD plus for that one was this this negative 0.275, and then the donor is going to be the 0.025. So we're going to do E prime equals 0. Negative 0.275 minus 0.025. And that's just going to be negative 0.3. And then you just got to plug this into the equation. So G equals negative N, and the number of electrons here is just going to be 2, right? Because it's just 2 for both of these, and we're combining them. So negative 2, F is 100, and then E is just going to be this negative 0.3. And I think the easiest way to do this is, one, the two negative signs here cancel. So this negative sign and that negative sign go away. 0.3 times 100 is 30. 30 times 2 is 60. So G, oh my goodness. G is going to be equal to 60 kilojoules per mole, if I'm not mistaken, or whatever the unit they want you to put there. Probably usually kilojoule per mole. Yeah, delta G is usually in kilojoule per mole. So give me kilojoule per mole, and then is it exergonic or endergonic? Endergonic. Why is it endergonic? Positive. Yep. What would the E have to be for it to be endergonic? And for it to be exergonic? Positive. Yep. What about the KEQ? The equilibrium constant.
No.
It's always positive for KEQ. What is the relationship between KEQ? Yes, greater than 1 if it's greater than 1, delta G is negative. If it's less than 1, it's going to be positive. Remember, it's the negative RT ln KEQ. This stuff could all show up again in your final, which is why I'm like saying this. So yeah, good job though, nice. Okay, this one is hard. This is kind of tough. But we'll go through it. So
Question that we had the last exam.
it's a similar style of question. It's not the exact same. It's a similar style though. So indicate by putting an X in the appropriate box if it occurs in the mitochondria or chloroplast. I'm an avid chloroplast hater actually. So I dislike plants a lot, but you know we're gonna get through it. Proton pumping. Both. Okay. What's the difference between the two in terms of proton pumping? Yeah, it's in the lumen, right? Which one's in the lumen though? It's the whole relation. Yeah.
Chloroplast into the
Lumen. Yeah. Yeah. What's the outer area called? Like, so what it pumps it into the lumen, where does it go afterwards? Stroma. Yeah. Stroma is like the thylakoid's like fluid, basically. Right? No, sorry, so it's this chloroplast fluid. Yeah. Okay. Yeah. FES center. What's an FES center?
Like mine, sulfur.
It's an iron sulfur. Yeah. So I remember I had a conversation with I think it was you about this. You don't have to memorize the exact crystal structure. You do have to know that it is a thing that gets reduced in complex 4, generally speaking. It's going to be in both. So it's just a general carrier of electrons. So every complex, right, has these different like carriers, right, that allow it to like carry and shuttle electrons. I don't know if you guys remember these from the slides. What's an example of this? I can pull up the slide afterwards if we need to. But like there's like FES, there's copper, there's like A0, A1, B1. There's all sorts of different like carriers within each complex that you don't have to know all of them. I think you should generally know like you should know generally what the order is. I can't remember off the top of my head. It's been a while since I looked at it. Um, but you should know generally what kind of things are in there. So if you like iron sulfur centers are just general reduction, like they're general electron carriers within complexes, so they'd be in both of them. Okay, oxygen reduction. Mitochondria. What does the chloroplast do? True, does not reduce oxygen. What does it do instead? Oxidizes water. Yeah, it oxidizes water and turns water into O2 gas. Believe it or not, guys, we actually breathe oxygen gas from plants. So that's where you get the oxygen gas from. We're oxidizing water and turning it into O2. And then we use the O2 in our mitochondria for cellular respiration. Um, this one's kind of stupid. Manganese cofactor. There's exactly one slide on this in your guys's. It's chloroplast, yeah. It's in I think it's photosystem 2. It is the first thing that accepts the electrons from water. It's like the manganese copper oxide complex. I'll show it afterwards if I get a chance to. I was trying to find this thing for so long. I was like, where is this? And I finally found it in your lecture slide. Because if it's not in your lecture slide, you're not going to be tested on it. But if it's in your lecture slide, even if it's like one small bullet point, it's fair game. So this is a classic case of it's one bullet point, it's fair game. So yes, yep, yep, yeah, that, yeah. But yeah, annoying. Okay, Pheophyton, chloroplast. Yep. I can't remember the exact location. I think it's also photosystem 2, if I'm not mistaken. Yeah, yeah. Yep. So also photosystem for also chloroplast. Carbon fixation. Chloroplast. Where does it occur in chloroplast? What cycle? Or what process? Calvin cycle. Yeah, and what enzyme does it? Rubisco. Yeah. Yep. Rubisco is the good old guy. And then for water oxidation, which one does water oxidation? We already talked about this. Chloroplast, right? Good. Heme groups. Both. So remember how I said like those A0, A1 complex, those Bs? Those are all hemes. Those are all heme containing compounds. Right? Hmm? Yeah, so the complexes, right? Remember how those complexes have like A0, A1, B1, C, all those things? Cytochrome C, for example, is a heme carrying protein. Yeah. So it's called A, B, and C because it's different types of hemes. That's why it's referred to as A, B, and C. They are not going to test you on the exact structure of the hemes. I guarantee that. If they do, you can come over here and start yelling at me. But they can definitely ask you like which ones have hemes in them. That's pretty reasonable. And you'd have to both of them have hemes. Both of them have like the A1s, the A0s, and all that jazz. So
They're in like all complexes.
I think it is in all of the complexes. I'd have to look at the image itself, but I'm pretty sure it's in the majority of them. Okay. Aldolase. Chloroplast. Where is aldolase in
Or like
It's in Calvin cycle, but which step of Calvin cycle? 3. It's in the massive carbon shuffle step. In that massive series of carbon shuffles, I'll pull that slide up if we have time at the end. But it turns glyceraldehyde 3-phosphate and DHAP into fructose 1,6 bisphosphate.
it makes citric acid.
Yep. So it's one of the first things to remember, right? In Calvin cycle, the whole point of doing that process is to make those 5 glyceraldehyde 3-phosphates and then it's to make 6 of them, shoot one of them off to make like sugars and other stuff, and the other 5 go back into the cycle to make RUBP. And in that thing of going from glyceraldehyde 3-phosphate back to RUBP, there's this massive series of carbon shuffles with transketonases. And all of those, the first step in that is the aldolase reaction to take one of the glyceraldehyde 3-phosphates, turn it into DHAP, and then combining a glyceraldehyde 3-phosphate with the DHAP to make fructose 1,6 bisphosphate. And then you go through the massive shuffling scheme. Yeah? Okay. Has double membrane. This one should be pretty straightforward. Both. Yeah, both have double membranes. Cool. Any other questions on this? I'll come back to it at the end, hopefully. Yeah. I think this is just a case of like, do you know or do you not? It's unfortunate because it's like, some of these are kind of dumb, right? The heme group one's kind of annoying. The manganese one is just plain mean. So it's like, if you straight up just might not know, and what can you do, I guess? I would say the rest of these are like, okay. Maybe the FES centers is kind of mean, but the rest of them I think you guys can probably work your way through.
So it's also because it's part of the shuffle.
So it's part of the carbon shuffle in Calvin cycle because of the fact that you have 2 3-carbon units that you have to turn back into a 6-carbon. Pentose phosphate pathway, you don't have. You have that. I actually can't remember. I'd have to look at the slide. I actually cannot remember off the top of my head if there is also that. If aldolase is present in pentose phosphate pathway. I mean, it is in the glycer. It's in glycolysis, right? Because pentose phosphate pathway is like connected to glycolysis. Because they're both in the cytosol. So by that logic, yes. But it's not in the mitochondria. I don't think there's not like a specific step within that shuffle that is aldolase, if that makes sense. Okay, these are some pretty straightforward round off these questions. 6-phosphogluconate is more reduced than glucose 6-phosphate. Is that true or false?
False.
False. What's the structure of 6-phosphogluconate?
I just know this deeper into the pentose phosphate.
It is.
You're getting less and less reduced as we're going through, right?
Yeah, so is it in the oxidative or non-oxidative pathway? Oxidative, and oxidative means oxidation.
Yes.
And the workflow of that pathway is going to be glucose 6-phosphate. Glucose 6-phosphate dehydrogenase turns it into 6-phosphoglucanolactone. And I covered this in my last lecture video where I reviewed this. I kind of explained why it's called glucanolactone. But a lactone is basically it's like it's a 6-membered ring where there is an ester present. So like, this is a lactone. And if you look at 6-phosphoglucanolactone, it has that. And so that's why it's called 6-phosphoglucanolactone. And so the glucose 6-phosphate dehydrogenase, right, that uses NADP+, turns it into NADPH. And then from there, we have 6-phosphoglucanolactone dehydrogenase, which opens up that ring conformation, and then you release a CO2 along with another NADPH. But I will go ahead and I'll talk about that later. I think I actually might have mixed that one up a little bit, but I'll talk about that later if we have time. Plastoquinone is an electron transport chain in the mitochondria. Is that true or false? Where is plastoquinone? It's in the chloroplast, right? What's the one in the mitochondria? It's ubiquinone, yeah. So they're actually they're relatives, but they're not the same thing. Coenzyme Q transfers things from complex 3 to 4. What does that? Cytochrome C. Ah! False! You and I circled the wrong thing after saying the right answer. Okay. But those make sense, right? Good there? Okay. Okay, these are just like multiple choice questions, but we're almost done, guys. Good job. Okay. For 4, a reaction vial contains ribose 5-phosphate and xylulose 5-phosphate. Okay. You guys do not need to know the exact structures of these things. What I will say is that if you see this like ose ending, it means it's a ketose sugar. And then if you see like anything else, like if like this xylulose, this ose thing usually means ketose. If you see anything else, it's usually an aldose instead. Right? So ribose 5-phosphate is an aldose. Xylulose 5-phosphate is a ketose. So you add an unknown enzyme and you find that the reaction produces glyceraldehyde 3-phosphate and another carbohydrate. So which one is correct? So we know that xylulose 5-phosphate and ribose 5-phosphate are both 5 carbon sugars, right? So we have 10 carbons total. If one of the products is glyceraldehyde 3-phosphate, we can't just delete the other 7 carbons, right? So we can't just delete them. So we have to have a 7 carbon sugar as our product. And if we're going from a 5 and a 5 to a 3 and a 7, what we're doing is we're removing 2 carbons from one of the 5 carbons and putting them onto the other 5 carbon.
You said both of those are ketone?
No, so this xylulose 5-phosphate is a ketose. And then ribose 5-phosphate is an aldose. So if we're doing that, right, what enzyme does 2 carbon transfers? Transketolase. Which one does 3 carbon transfers? Transaldolase. So it cannot be a transaldolase. So go away. So let's see here. If this is the one where I always keep forgetting, but I'm pretty sure it has to be, yeah. So if we start with an aldose and a ketose, right? Generally speaking, we have to end with an aldose and a ketose. That's generally how the workflow goes when you have these enzymes. So, is glyceraldehyde 3-phosphate an aldose or a ketose? It's an aldose, so we have to end with a ketose as well, right? Start with an aldose, we end a ketose, we end with an aldose and a ketose. And so, if that is the case, it has to be C, because we just said it has to end with a ketose and not an aldose. Good?
You said it has to end with a ketose, right?
Because we started with an aldose and a ketose, and the product that we know came out is an aldose. The glyceraldehyde 3-phosphate is an aldose, so that means that our other product has to be a ketose.
Okay, so that means that you're only using one of those two to react with the glyceraldehyde?
No, the point is you put 2 5 carbons in, right, and you get a 3 carbon and a question mark out. You don't know what the question mark is. But you can't just delete carbon, so it has to be 7 carbon sugar. Did you have a question as well?
Yeah, do you do like transfer to ketose and
That's a good question.
or it's not?
I don't think I've ever seen a case where it's a transketolase with someone has to check the slides for me on the pentose phosphate and the Calvin cycle stuff, but I don't think I've seen that. I don't think I've seen a transketolase reaction with a double ketose or double aldose. I think it has to be between a ketose and an aldose. So, which one of the following mechanisms couples the light reactions to the dark reactions? Which one, guys? What are we thinking? Okay. Why?
Because when in the dark reaction well, like a reaction where it would reduce the pH and make that I don't know stop the reaction.
Thyroidoxin. So there is a pathway. So the light dependent reactions, right, is the electron transport chain. What do we produce from the light dependent reactions? What are the things that we make? ATP, NADPH, and technically you make oxygen as well, right? But yeah, so NADPH. Um, NADPH is produced from the light dependent reactions. And for the light independent reactions, quote unquote light independent, right? All of those enzymes need to be in their reduced state to be in an active form, right? A lot of them do. I can't remember these. I think fructose 1,6-bisphosphatase has to be reduced. There's a big slide that goes over that. But those enzymes have to be in a reduced state to do that. And the way that they do that is through thioredoxin. So thioredoxin is like this reducing agent. So what you do is you take the electrons from ferredoxin, and from ferredoxin, you dump those electrons onto thioredoxin. You reduce this like thioester bond or this disulfide bond that activates thioredoxin, and then thioredoxin goes in and starts reducing everything else. I'll try and pull that slide up at the end here, but the answer would be D. The other ones just don't make sense as well. You could maybe try and argue for the phosphorylation ones, but you guys never talked about any kind of phosphorylation when it came to any of these pathways. There's no maybe PDH has some phosphorylation with PDH kinase and PDH phosphatase, but there's no phosphorylation stuff with plants. Right? That makes sense? Other than ATP synthase. For 6, from the enzyme listed, identify the one correct sequence for the regeneration phase. So this is the Calvin cycle, specifically that carbon shuffle. Does anybody remember the ordering?
Aldolase goes first.
Aldolase does come first. So we take our DHAP and our glyceraldehyde 3-phosphate and we combine them together. And what do we make from that? Fructose 1,6-bisphosphate, right? Fructose 1,6-bisphosphate. Is it D?
You have to phosphatase.
You have to phosphatase it first, yeah. So it wouldn't be D. So it's gonna be C. Where does the kinase come into play?
I don't know.
You should remember. Where's the kinase? Ribulose 5-phosphate. Why do we need the kinase? And why do I need that? To keep the cycle going, right? Because the thing that starts the whole cycle in the first place is ribulose 1,5-bisphosphate. And so by adding that kinase in there, I go from ribulose 5-phosphate back to ribulose 1,5-bisphosphate. And I can do the cycle all over again. And do you remember, the transketolases are just everywhere. Right? These transketolases are all over the place. The cetoheptulose, right, the 7-carbon sugar, where you transfer the 2 carbons into a glyceraldehyde 3-phosphate, that's another transketolase reaction. There's a whole bunch of transketolase reactions. Again, I think it's better if I try and show you guys, but we'll see if we have time. And this is the last one. Plastocyanin takes part in photosynthesis in plants. Which of the following describes its function? Which one are we thinking here? Okay, so you put anybody else? Anybody else have any answers? So we have D as an option. A, okay. Anybody else got any options? Okay, so DNA. Okay. So let's go over that. So what are the carriers that we know? So from photosystem, it's like for the photosystems, right? What's like the first like carrier that we know? So we know plastoquinone and plastocyanin. Where does plastoquinone operate?
Like before.
Right, so it's before. And we're looking at plastocyanin. Where does plastocyanin operate? After B6F. Or this, yeah, B6F complex. So plastoquinone carries things to B6F, and plastocyanin takes things from B6F to ferredoxin. Right? Remember the quinones, so the quinones are related, right? They do the same kind of carrying job. So in the mitochondria, it goes from 1 to 3 and 2 to 3. in the plants, it just goes from photosystem 2 to, I think it's photosystem 2 and photosystem 1 to, or sorry, photosystem 2 to B6F, right? So, in this case, it would actually be A, because it is oxidizing the B6F complex, reducing itself, and then donating its electrons later on in the pathway. Well done, guys. End of the exam. Yeah, this one's a pretty challenging test. Yeah, I wanted to do the harder one because I think my exam from last year was a little bit on the easier side. So, yeah.
Ooh,
I think it's a mix of the two profs. So both Brockerhoff and Holt wrote it. So I don't think like 'cause Brocker that was Brockerhoff's section when she taught it. So Holt only did the first exam. Yeah. So yeah.
I was doing stuff.
Anyways, I wanted to show you guys when I did these. You're free to leave, by the way, if you want to. I'm not gonna force you to stay here, but um. I wanted to show, and I posted all of my videos, by the way, they're all up to date for your exam. It's on the announcement. I posted the link to that. I definitely do a lot more in-depth, like, review of those, so. But yeah, so, so see FES here. FES. And then, these A1 and A0 things, these are hemes. They're called A0, A1 because there's different forms of the heme. But they're all heme groups. So if you see like A0, A1, C, B, heme groups, they're all heme groups. And then FES is photosystem 1 in this case. Let's see here. Here's here's the manganese. If you want this, there's your manganese. So that's there. It's in photosystem 2. I want to show the carbons. Where's the carbon shuffle? I thought they showed it here. Did they not show it in this one?
She knew that.
They don't. Oh, it's in the next lecture, isn't it? It's lecture 20. Do I not have 26 in here? Oh, I do. There it is. I'll duplicate this. You can see all my rigorous circling of these things when I was recording my videos. Okay, yeah, and this is just the reverse of glycolysis. That's the other thing, right? This is literally just the reverse of glycolysis. The enzymes are exactly the same. All right, phosphoglycerate kinase, 1,3-bisphosphoglycerate, GAPDH. So. And also the other thing that like remember that TPP is the cofactor for transketolases, but not for transaldolases. Right? What is TPP usually a cofactor for? What kind of reaction? Decarboxylations. This is not a decarboxylation, it's a transfer reaction. But it's also responsible for a lot of transferase activity.
You said ketolase, not aldolase? Or
Not aldolase. It's transketolases, but not transaldolases.
no. Just a cofactor for PPP, that's all.
TPP is the cofactor for transketolases, yeah. It's like a very hyper-specific thing that you need to know. But you'll learn in 441 that transaminases also, like a transfer enzyme, also use TPP as a cofactor. So. But here, okay. You can see all the circling I've done for this? Okay. So, can you guys read those? It's kind of hard to see. I guess I'll like try and walk through this a little bit. How much time do we have? Like 5 minutes. Okay. Here are the 3 very exergonic steps that I was talking about. So fructose 1,6-bisphosphatase, cetoheptulose 1,7, and then ribulose 5-phosphate kinase. So I'll try and walk through this from the top. So when you go through Calvin cycle, right, and you go to that 5 sugars when you make the 5 glyceraldehyde 3 phosphates in the end, right, you have a glyceraldehyde 3 phosphate. How do I make this? What's the enzyme that does that? Trilose phosphodiisomerase, right? So if I have glyceraldehyde 3 phosphate or TIM or whatever you guys call it, right? Yeah. So I can make a dihydroxyacetone phosphate. And then I combine these two with aldolase. And this aldolase is located where? Cytoplasm. It's not in the cytoplasm. Where is it? Where does the Calvin cycle happen? It happens in the chloroplast, in the stroma of the chloroplast. So you have an aldolase in the stroma of the chloroplast and also in the cytosol of your cell. Because remember, the chloroplast is an organelle inside of the cell. So two separate aldolases, right? So we do this, we have our aldolase, we do our fructose 1,6-bisphosphate, we release a PI, we make this. Very exergonic step. Very exergonic. Okay? And then we go here, we do this, we have a transketolase reaction where we take, so this is a 6-carbon sugar, that's a 3-carbon sugar. So if I have a 6-carbon sugar and a 3-carbon sugar, I expect to go to a 5-carbon sugar and a 4-carbon sugar. Right? You're not going to do a transketolase reaction for no reason. The purpose of these transketolase reactions is to make 5-carbon sugars. So every time you see the transketolase reaction, you should be expecting that one of the products, at least one of the products usually, is a 5-carbon sugar. Right? Or if it's like the reverse reaction and you start with like a 5 and a 5, it's going to be like a 7 and a 3. Something like that. Right? So transketolase here, we have a fructose 6-phosphate. We go to erythrose 4-phosphate. Erythrose 4-phosphate is 4 carbons. So we're going to take 2 carbons from this and add them onto glyceraldehyde 3-phosphate, make xylulose 5-phosphate, right? And then from this, we just do ribulose 5-phosphate epimerase, which is just switching one of the chiral centers. And then we make ribulose 5-phosphate, and then we use a kinase on it. So these kinases, it doesn't say kinase, but these kinases here are very exergonic as well. Very exergonic. And these are some of the, I believe these are some of the enzymes that are actually regulated by that like thyroidoxin pathway. So thyroidoxin is helpful for these 3 steps as well, if I'm not mistaken. And then for that, we're back here for another aldolase. We're taking a 3-carbon and a 4-carbon, and we're combining them into a 7-carbon. We remove a phosphate. We're here. We have a 7-carbon and a 3-carbon, which is 10 carbons. We do a transketolase. We end up with a 5 and a 5. We do the epimerase again here to make ribulose 5-phosphate, and then we kinase it. And then here we have a ribulose 5-phosphate. I isomerize it because this is the aldose form. We turn it into the ketose form. And then we add ATP to it, right? So a lot of information very quickly. But if you want like another rundown of it, I covered it in my videos. So just watch that and skip to the end. And I did, or not skip to the end, skip to the middle somewhere. And I kind of went over this, and you can like repeat that as many times as you want, to try and get this down. Right, but yeah, I would say like you should memorize like or have an idea of generally what enzymes are here, what they do. Right, so aldolases combines things together, transketolases transfer 2 carbons, kinases do kinase things, and stuff like that. And the last, here's the thyroidoxin pathway. If you were curious of what it does. It's basically like electrons from the ferredoxin reduce thyroidoxin, and the thyroidoxin activates some of the enzymes. And here are the enzymes that are activated by reduction by thyroidoxin. So, yeah. That's 7, though. GG, guys. We're done. Yeah. I'll take other questions if people have questions, but yeah. And then here's the oxidative portion of penultimate pathway. Oh man. Yeah. So I mean, just like real quick, see this here? Notice how it turns into a lactone here? Right, it's an oxidation because we're making another carbon bond. Use NADP plus NADPH. 6-phosphogluconate, 6-phosphogluconolactone, 6-phosphogluconate. Notice how this is now in the it's a hydrolysis, so we're actually opening up the ring. And then this last step here is a decarboxylation reaction where we also make another NADPH.
Do you listen to for that?
That's a good question. I'd assume so, but actually, they didn't mention that, did they? You probably do. You probably do, but I actually have no idea for that one. Yeah,
Question.
yeah.
You got 6 lectures, right? If there was one lecture to just sacrifice,
Okay. One lecture to sacrifice all your time for?
no, to just
Oh, to bin off. Like,
put it aside. Which one?
which lectures did you guys have again?
Because like we went from PDH all the way to this.
Let's see here. I actually have no idea. Hold on. Let me.
And PDH, we had Chiastic cycle, electron transport chain.
You're naming off some pretty important ones right now. I'm not gonna lie.
Like I don't
I
know.
feel like all of those are quite important. Let me.
Just want to sleep, man.
Yeah, you're not gonna sleep, man. I'm sorry. Let me actually double check the. Let's see here.
Also class.
Yeah, it's also linked to a playlist here if you guys want to watch those. But this is how I actually keep track of what lectures you guys have done. Calvin. Wait. I think if I was to say maybe oxidative phosphorylation. I feel like you don't. What was covered in this
Essentially,
lecture?
what's
Was it?
happening is that every
Was it?
the pluses you
Huh?
have on
It's unlisted, so it's private. Yeah, so people can't watch. Like people.
of
Yeah, bro, I'm not putting it on the IC page because it's like so the formatting is so jank.
Why don't you just like turn it like you're just already being like another open tutor? You should just post it, get like a bajillion views, and like
I'm not gonna get a bajillion views.
you guys feel like you're really weird.
I would skip this lecture. Yeah. If I was to say like a lecture you should skip, it'd probably be this one.
So it was gonna be synthesis.
I just think that you guys they could totally test you on like the different subunits of ATP synthase, but like that's relatively low yield. I want to say it's low yield. I want to say it's low yield. I think the other stuff's far more important. Um,
What about the inhibitors though? Like,
yeah,
so I don't. But like first.
yeah, yeah. I think I can't remember. There's a slide I think where they talk about like a couple of different inhibitors. I can't remember where it is though.
Or actually, that graph you had up.
Huh? It'd probably be in the ETC lecture, right? If you didn't have rotenone, I might be remembered from my year. I did have rotenone when I took the class. But if you guys didn't have rotenone, you can probably ignore that. But I just remember having rotenone as one of the things I had to know. I would. It doesn't hurt to know though. Yeah. Yeah.
That graph right there.
Yeah.
How do we interpret that? Like, if we're given a question on the exam like that, like they would give us like the graph or something, and be like, "Oh, what does it mean?" How
The same way you interpreted the one in the test, right? Like because we interpreted.
Oh, the PDH one.
No. The same way we interpreted. Nope, that's genome.
What is that?
What? Bro, why is this guy? Yeah, sure.
Like if you were us in our shoes right now, and you were about to take exam, would you for like answering all the questions, or would you?
Oh, yeah, because your formatting is different. Like you get one question that you can like sack off, right?
Yeah.
I would do the ones that you for sure can answer first. But like the thing is, like the issue with a lot of these tests and like being students is that we're stubborn, and then we look at the first question and we start doing it, and then we're like, we can't finish this question, guys. We don't move on. It's just kind of a habit you have to get rid of, unfortunately. I would say like try every question, and if you notice that there's like one question that you're like, what the actual hell is happening? Go to the other questions, do those, and then come back because you do get that one question drop, which is helpful. That's really helpful.
Why would you know?
Yeah, did you not read your own syllabus?
Oh,
Yeah, yeah.
like, this is something. Oh, there.